In this video, we'll look in more detail at polar reactions, reactions of polar compounds that proceed by heterolytic bond-breaking events. And these are the reactions of nucleophiles with electrophiles that we just saw. And we can map these polar reactions onto the 4 classes of reactions that we saw in the last video. First, an addition reaction we also call a nucleophilic attack reaction when it deals with polar compounds. This is the reaction of a nucleophile that attacks an electrophile to form a single new product. Here the nucleophile is bromide, which is negatively charged and has lone pairs. And the electrophile is the carbocation, or positively charged carbon species. In these reactions, and all reactions, we want to make sure we charge balance the reaction, meaning that the overall charge on the left side, the reactant side, is the same as the overall charge on the right side, or the product side. Here on the left, we have 1 positive and 1 negative charge in the reactants, so the overall charge is 0. And on the right-hand side, we have a neutral molecule with an overall charge of 0. So our reaction is charge balanced here. Okay, the second class of reaction is an elimination reaction, which is when a single reactant splits into 2 products. And for polar reactions, we call this the loss of a leaving group. When this reaction happens, the bond breaks heterolytically, and both electrons from the bond end up on the leaving group. In this case, the leaving group is bromine. A leaving group is a group that's able to effectively stabilize negative charge, something that's electronegative, like a bromine or an oxygen. Third, we have substitution reactions. And these are reactions where 2 reactants combine to form 2 new products. We can also think of these reactions as a group on the reactants changing places from one reactant to the other. And in this example, that group is the hydrogen. It changes places and moves from the chlorine to the oxygen. In this reaction, the oxygen is the nucleophile, and the hydrogen, or the proton, is the electrophile. And this is an acid-base reaction we already saw, and acid-base reactions are some of the simplest forms of polar substitution reactions. When the nucleophilic oxygen anion attacks the proton, a new bond is formed between the oxygen and the hydrogen, and the bond between the hydrogen and the chlorine breaks heterolytically. Both electrons in that bond move to the chlorine, and this movement of both electrons to the chlorine results in a negative charge on that atom. The fourth and last category of reactions that we'll look at are rearrangement reactions. And remember that these are reactions in which a single reactant undergoes bond rearrangement to form a new product. And for polar reactions, our most common type of rearrangement reactions are carbocation rearrangements. So remember that a carbocation is a positively charged carbon. And the stability of carbocations increases with substitution, meaning that more substituted carbocations are more stable than less substituted carbocations. And so carbocations can undergo rearrangements to form more stable carbocations. And that's the only way a rearrangement will happen, a less stable carbocation rearranging to form a more stable carbocation. When a carbocation rearranges, it's the nearby groups that move. And a hydride is the most common group that will move, and we call this a hydride shift. Remember that a hydride is a hydrogen and 2 electrons, or both electrons in the bond. So when it shifts to carbon with a positive charge on it, the carbon that originally held the hydrogen is left with a positive charge. Remember, we have to charge balance, so if we start with a positive charge in our reactants, we end up with a positive charge in our products. A few things to note here. First, the hydride will only shift to form the more stable carbocation. Here we started with a secondary carbocation and ended up with a tertiary one. The tertiary is more stable than the secondary. Second, a hydride is only going to shift 1 position over. It will only come from the carbon next to the carbon cation. So if there is no hydrogen on the adjacent carbon to shift, then a methyl group can shift instead. This is harder than a hydride shift, so it will only happen if there is no hydride to shift. And a methyl shift functions the same as a hydride shift. The methyl group and the electrons in the bond shift 1 position over to the positively charged carbon. This leaves a carbocation on the carbon that originally held the methyl group. A methyl will only shift if the new carbocation is more stable than the original carbocation. And it will only shift if there are no hydrogens on the adjacent carbon for a hydride shift to occur. Let's do a quick concept check. Classify the polar reaction shown below, then draw the appropriate curved arrows to map the flow of electrons. Okay, first, to classify the reaction, we'll determine how many reactants are converted into how many products. Here we have one reactant going to two products. So this is an elimination reaction, or the loss of a leaving group. Okay, now to draw the arrows, I like to identify which bonds are broken and which are formed. And I'll do that in yellow here. We see the carbon-chlorine bond is broken, and those electrons end up on chlorine. We see that with the negative charge. And a new carbon-oxygen pi bond is formed, and that's formed with the negative charge on oxygen. So I'll draw my arrows beginning at the oxygen anion. Those electrons move down to form a new pi bond, and then the carbon-chlorine bond breaks heterolytically to release the chloride anion, the good leaving group. And remember that these are double-headed arrows to indicate the flow of two electrons. We'll end here by answering the question we posed at the beginning, to classify the reaction shown and then draw the curved arrows to map the flow of electrons. We'll approach this question just like we did the last one. To classify the reaction, we'll determine how many reactants and products we have. And here we have two reactants forming two products. So this is a substitution reaction. Then to map the electron flow, I look for the bonds that are formed and broken. The carbon-chlorine bond is broken, and a new carbon-oxygen bond is formed. I also like to identify the nucleophile and electrophile. And here the anionic oxygen is the nucleophile, and the carbon bound to the chlorine is the electrophile. The nucleophile attacks the electrophile, so we draw a double-headed arrow originating at the oxygen lone pair and ending at the electrophilic carbon. And then the carbon-chlorine bond breaks, and the chloride leaves with both electrons from the bond. So we draw another curved arrow originating at the carbon-chlorine bond and ending at the chlorine.